All right, so moving to 2.3, we introduce a new property here, which is called entropy, and our symbol for that is delta S. So entropy sounds really similar to enthalpy, but it's actually totally different. It's a little bit of an abstract concept, but I really think the key to understanding it is to think of it as a synonym for disorder. So if something has high entropy, it's very disordered and chaotic. And if something has a low entropy, then it's very neat and ordered. So as an example, a solid has the lowest entropy, then a liquid, and then gas has the highest entropy. And that's just because of the way that the particles are arranged, which you can see in the picture here. And then with gases specifically, when you have more moles of gas, it is the same thing as having more disorder, so higher entropy. But we'll talk about this a bit more when I do the practice question in a few moments. Okay, and so remember those laws of thermodynamics that I talked about? Well, the second and third ones are actually all about entropy. So let's start with the second one, which says that every spontaneous process increases the entropy of the universe. So what this is saying is that the universe will favor processes where the entropy increases. So if you think about this mathematically, it means that the final entropy will be greater than the initial entropy. So the universe favors delta S values that are positive or greater than 0. Again, this is pretty abstract. So the best analogy is to think of your bedroom. So how many times have you not even been trying for your room to get messy and it just does because you're rushing around to get ready for class or whatever. But does your room ever just spontaneously become clean and neat? No, the universe doesn't favor that. You'd actually have to put in extra effort and energy if you wanted that to happen. So just like your bedroom, the universe always favors going more towards disorder or a positive entropy. All right, so now that we have the conceptual understanding of entropy, we are going to bring in a calculation, standard entropy change. But the good thing is that this calculation is actually exactly the same as the enthalpy one that Josh introduced. But instead of using enthalpy of formation values, you'll be using standard entropy values, which would be given to you in a different table. And just a little helpful fact is that these standard entropy values are actually calculated based off the third law of thermodynamics, which says that a perfect crystal has 0 entropy at a temperature of 0 K. So you don't really need to memorize all the details of that, but I really just wanted to make sure that I was kind of checking off all the boxes in terms of going through the significance of all 3 laws of thermodynamics. But anyways, back to the calculation. It's exactly the same as the standard enthalpy of formation one. So you're doing the sum of the products minus the sum of the reactants. Just remember to multiply by your stoichiometric coefficients if necessary. And also just keep in mind that the units for entropy are different from enthalpy. So enthalpy we saw was kilojoules per mole, but entropy values are usually in joules, and they also have this temperature aspect in there as well. Okay, so let's do an entropy practice question here. So this one says, which one of the following reactions will have delta S of the system greater than 0? So remember that if the change in entropy is greater than 0, then that means that the final entropy should be greater than the initial entropy, because when you do the difference between them, it should be a positive number. And so remember that a higher entropy means more disordered, and then the lower entropy will mean more ordered. So let's go through each of these scenarios and see if any of them or which one of them fits that. So starting with A, we see that we have liquid, gas, and then on this side we have liquid and gas. So our states are kind of the same, but if we just look at the gas specifically, here we have 8 moles of gas, and here we have 5 moles of gas. And so remember I said the more moles of gas you have, the more disordered the situation is. So here we have an initial situation that's more disordered than our final situation. That's the opposite of what we want. So we can eliminate A. Looking at the next one, again, everything's all gas, so let's count our numbers. So we have 2 moles of gas plus 1 mole, that's 3 on this side, and just 2 on this side. So again, we have an initial situation that's more disordered than our final situation, so that also will not be our answer. Looking at this one, we don't have any gas, so we're not counting moles, but instead we're looking at the situation as a whole. So here we've got some ions dissolved in solution, so basically liquid, and then we've got a solid. The solid is more ordered than having like a bunch of ions disassociated in a solution. So again, this is the opposite of what we want because our final is more ordered than our initial, so not C. In D, we start with a liquid and then it becomes a gas. Gas is more disordered than liquid, so our final state is more disordered than our initial. That is what we want. So it's looking like D is our answer, but let's just check the last one. So again, we're all gas here, so we're going to be counting the number of moles. And we've got 1 mole here, 1 mole here, 3 moles here, and then just 2 on this side. So our final state is more ordered with 2 moles than our initial state, which has 4 moles. So again, that's not what we were looking for. So that confirms that D is our answer. So questions that have to do with entropy, and they're asking you if it's a positive or a negative entropy, you want to look at first the different states that you have, but if everything's kind of equivalent there, then you can start looking at the number of moles of gas and counting those up.